Look up at the night sky tonight. What do you see? Stars, galaxies, nebulas. It looks completely crowded, like the universe is packed wall to wall with stuff. Every image of space looks busy, filled with planets and light. But here's the biggest secret about the cosmos. Almost all of it is completely empty. We are talking about the most absolute, profound nothing you can imagine. The tiny amounts of matter that do exist control everything, but the vast majority of space is cold, dark vacuum. This feeling that space is full is a massive trick played on us by distance and light. Tonight we are going to expose that trick and find out why this simple nothingness makes the universe possible and stable. Think about what empty even means in physics. When you use that word here on Earth, it usually means removing the air in a container to create a vacuum. But even the best vacuum we can create in a lab is full compared to outer space. When we talk about space being empty, we are really talking about the absolute scarcity of ordinary matter, the atoms, gas, and dust that make up everything you can touch. For a moment, let us compare the density of Earth's atmosphere to space. If you take a cubic meter of air right now, it contains roughly 10 to the 25th power particles. That is a 1 followed by 25 zeros. That is incredibly dense, but let us look at the space right outside our solar system, in the interstellar medium of the Milky Way galaxy. In that same cubic meter, you might find around 10 to the 6th power articles, maybe a million. That sounds like a lot until you compare it to the air right here. It is millions of billions of times less dense than the air you are breathing. Now, that emptiness is what allows light to travel for billions of years largely undisturbed. If space were dense, like water or even our atmosphere, light would scatter instantly. But because space is so barren, light journeys across impossible distances, bringing us pictures of the universe's past. We see this profound emptiness even when we look at vast structures like galaxies. From far away, quasars, which are incredibly energetic centers of distant galaxies powered by supermassive black holes, look like stars. They are extremely compact, yet they are shining with the power of many galaxies combined. This tiny, bright point leads us to believe that the space between us and them is also full of interesting things. But the reality is that the distances are so great that these points of light only serve to emphasize the void that lies between. We confuse the light from distant, bright objects with the presence of matter spread throughout the space. The light from distant, massive objects merely highlights the vacuum by traveling across it. The emptiness itself is what determines how light gets to us and how far we can see. The feeling that space looks full but is not is based purely on the objects we can see, which are the exceptionally luminous ones. These objects, like stars and accretion disks, are generating massive amounts of energy and light. When we look out and see stars, we are only seeing the tiny specks where matter has managed to accumulate, fuse, and radiate energy. The rest is just the background of nothing. This is the great paradox. The only reason we can see anything at all is because everything else is nothing. This lack of matter is the reason why astronomers needed special equipment just to measure the true composition and density of the medium in our own galaxy, starting with early radio and X-ray telescopes. They were trying to measure the truly scant amount of material that resides even in the busy parts of the cosmos. So we know space is overwhelmingly empty, but how does that emptiness break down across the cosmos? Even within this vast nothing, scientists divide space into layers based on how little matter they contain. The two major categories we use are interstellar space and intergalactic space. The difference between them is enormous and shows just how rapidly the density of matter drops off the moment you leave a galaxy. Let us start close to home, interstellar space. This is the space inside our galaxy, the Milky Way. Even the Milky Way, which holds hundreds of billions of stars, is mostly empty space. But the emptiness within a galaxy is still relatively dense compared to the regions outside it. The space inside the Milky Way is filled with something called the interstellar medium, or ISM. This ISM is the extremely thin soup of matter that connects everything within the galaxy, and it is crucial because it is the raw material for forming new stars. This medium is mostly made up of highly diffused ionized hydrogen atoms, along with microscopic cosmic dust and cosmic rays scattered throughout thick gas clouds. We live inside one of the relatively low-density regions of the ISM, known as the local interstellar cloud, which is about 30 light-years across. Even this cloud is held within an even larger cavity called the local bubble, which spans about 1,000 light-years. These bubbles and clouds are dynamic, highly complex structures. For instance, our solar system travels through the local interstellar cloud, and our Sun generates the heliosphere, a large protective magnetic bubble that pushes against the surrounding ISM, acting like an invisible shield against cosmic rays and other material. This boundary, known as the interstellar space border, is where the Sun's influence gives way to the general galactic medium. So, while interstellar space feels empty to us, it still contains enough material ionized gas, dust, and magnetic fields to interact strongly with things like the solar wind. The density in the ISM is roughly equivalent to a laboratory vacuum, which is still busy enough to interact with light and matter over extreme distances. Now let us travel out of the Milky Way, away from all its stars and gas clouds, and look at intergalactic space. This is the space that separates galaxies. This is where the term almost perfectly empty truly applies. Intergalactic space is many orders of magnitude more empty than interstellar space. Between galaxies we find gas, but it is much thinner and more rarefied than the ISM, existing as a thin cosmic fog. The visible matter density here drops down to possibly 1 hydrogen atom per cubic meter, or even less. Why the huge difference? Galaxies gather matter gravitationally. They are massive gravitational traps formed by dark matter halos that collect gas, stars, and interstellar material. When you leave that gravitational well, the matter quickly thins out to almost nothing. In fact, a dark matter area around the Milky Way extends for about 2 million light-years, but the visible components drop off much faster. The sheer lack of atoms in intergalactic space is what makes studying distant cosmic structures so hard, unless they are exceptionally bright like quasars. Because the intervening space is so empty, the light from these distant sources travels almost entirely unobstructed. The extreme vacuum of intergalactic space is the ultimate expression of cosmic nothingness, making the already thin interstellar medium seem positively crowded by comparison. It is the blank canvas upon which the greatest features of the universe are painted. The extreme emptiness we just talked about in intergalactic space is the very reason why galaxies, despite their immense gravity and speed, do not crash into each other constantly, making the universe look relatively calm on the largest scales. Think about the scale. Our Milky Way galaxy is huge, about 100,000 light-years wide, and it contains 100 billion to 400 billion stars. Now imagine a single star, like our Sun. If the Sun were reduced to the size of a grain of sand, the nearest star, Alpha Centauri, would be a separate grain of sand about 4 kilometers away. That is about 2.5 miles. There is nothing but vacuum in between. This distance-to-size ratio is why space appears empty. Even within the dense region of a galaxy, stars are not packed together. They are separated by immense gulfs of vacuum. This is the key to understanding galactic collisions. While galaxies appear dense and solid in images, they are fundamentally massive clouds of distant stars and gas. The space between stars is so enormous that when two galaxies collide, stars rarely, if ever, actually hit each other. It is more like two immense swarms of gnats passing through one another. The most famous example is the inevitable crash between our Milky Way and the neighboring Andromeda galaxy, M31. Andromeda is currently located about 2.5 million light-years away from us. However, the two galaxies are gravitationally bound, and they are hurtling towards each other at about 250,000 miles per hour. In roughly 4.5 billion years, they will merge. This event, often called a cosmic traffic accident in theory, will dramatically change the structure of both galaxies, eventually forming a single, massive elliptical galaxy. But here is the most surprising fact about this future catastrophe. Most experts predict that this galactic collision will not have a significant impact on our solar system. Our Sun and planets will likely survive the merger intact, simply because the galaxies are primarily made of empty space. Individual stars and planets will be rearranged into new orbits within the resulting combined galaxy, but direct stellar impacts will be incredibly rare due to the sheer lack of density. To grasp this scale, consider the supermassive black holes located at the centers of galaxies. Our own Milky Way has Sagittarius A at its core, estimated to be 4 million times the mass of the Sun. Even this gigantic object, responsible for ruling the motions of stars around it, is tiny compared to the size of the overall galaxy. One expert suggests that if a galaxy were the size of Earth, the massive black hole at its center would be less than 1 inch across. The emptiness surrounding that tiny mass concentration is astronomical. This inherent emptiness is also what controls galactic growth. Gas and dust are the fuel for star formation and black hole growth. If the space were dense with gas, star formation would be completely out of control. Instead, the emptiness ensures that the distribution of gas and dust is patchy in giant molecular clouds and filaments, which creates the conditions for measured star formation rather than one massive, instantaneous stellar birth across the entire galaxy. The enormous vacuum provides a protective buffer that prevents cosmic violence from consuming all matter instantly. The immense emptiness of space is far from passive. It dictates the fundamental rules of existence on a cosmic scale, particularly how energy travels and how objects move. This deep vacuum affects everything from light and heat transfer to the engineering of human travel. First, let us look at how heat works in this void. On Earth, heat travels mainly through convection, transfer via fluid movement like warm air rising, and conduction, transfer via direct contact. In the vacuum of space, neither of those mechanisms can work because there is no medium to conduct heat or gas to convect it. This creates an extreme engineering problem for objects like the International Space Station, ISS. The ISS faces massive temperature extremes. When facing the Sun, it can reach over 250 degrees Fahrenheit, but when in shadow, it plunges to minus 250 degrees. To manage this, the ISS must rely entirely on thermal radiation to shed heat. This process involves radiating heat away as infrared light into the deep, cold vacuum. The station uses large radiators and an internal ammonia fluid loop, which is vital because, unlike water, ammonia remains liquid at the extremely cold temperatures encountered in the Earth's shadow. The lack of matter in space makes heat management an existential challenge for human habitats. Next, consider light and other forms of radiation. The emptiness is what permits light to travel over cosmic distances. When astronomers observe the universe, they are usually looking at electromagnetic waves, radio, infrared, visible light, which are generally oscillations of electric and magnetic fields. These waves are often easily absorbed and scattered by matter that intervenes between us and the source. This is why observing the center of our own galaxy, the Milky Way, is complicated. The view is blocked by layers of dust. However, the emptiness of space is so profound that other signals like gravitational waves and neutrinos travel through almost completely undisturbed. Gravitational waves, which are oscillations of the very fabric of space and time, are never significantly absorbed or scattered by matter, even when originating from the Big Bang era. Neutrinos, highly penetrating particles created in events like supernovae, stream through space virtually unscathed. This remarkable quality makes them perfect messengers for studying the universe's first second, an era when the universe was too dense and hot for light, photons, to travel freely. The cosmic microwave background radiation, CMB, only brings us a picture of the universe when it was 380,000 years old. But gravitational waves and neutrinos bring us information from much earlier epochs because the emptiness allows them to travel. Finally, the emptiness of space fundamentally affects travel. There is no air resistance, no atmosphere, and nothing to push against. This means any object in motion stays in motion, Newton's first law, but also that travel requires constant energy output for changing direction or speed. Spacecraft like the Dragon capsule rely on specialized thrusters, Draco thrusters, for orbital maneuvering and attitude control. If space were full of dense matter, travel would be impossible due to extreme friction and heating. And if space were full of gas, the ISS, which moves at 17,500 miles per hour, would be incinerated immediately. The profound vacuum is required for high-speed orbital mechanics and deep space missions. The great emptiness is not a mistake or a flaw in the universe. It is a feature that maintains stability and regulates the structures we see. If space were not almost perfectly empty, the consequences would be catastrophic, leading to a universe unrecognizable to us now. Firstly, consider how this emptiness enforces cosmic stability. Matter, even the sparse gas clouds in galaxies, is the fundamental fuel for structures like stars and black holes. If this fuel were easily accessible everywhere, the structures would grow chaotically and consume themselves rapidly. This concept is most clear in the love-hate relationship between supermassive black holes and their host galaxies. When gas and dust fall onto a black hole, friction heats the material violently, creating an accretion disk that radiates massive amounts of energy, often outshining the entire galaxy. This energy, released as X-rays and highly collimated jets, acts as a sculptor. It pushes surrounding gas away, preventing the galaxy from growing too large or forming stars too quickly. This feedback mechanism regulates growth. The black hole, in essence, eats enough fuel to blast away the remaining supply, which then leaves the galaxy quiet or dormant, like our own Milky Way, which has a relatively quiet black hole at its center. The emptiness ensures that this fuel intake is sporadic and localized, allowing for stable, long-term existence. Now picture a universe where space is not empty, where interstellar and intergalactic space were as dense as Earth's atmosphere, or worse, the interior of a neutron star, around 10 to the 14th power grams per cubic centimeter. If space was suddenly filled with a dense medium, one heat catastrophe, energy would be transferred instantly through conduction. Planets, stars, and galaxies would lose heat rapidly, cooling them towards absolute zero. Or, conversely, if the background medium were hot, like the 10 million degree gas seen in some supernova remnants, everything would instantly equalize to that searing temperature. Any complex chemistry or life would cease to exist due to thermodynamic chaos. 2. Obstruction of sight. Light would scatter instantly in such a thick medium. All long-range observation would end. We would not be able to see beyond our own solar system, as visible light would be absorbed and diffused instantly, much like trying to see across a thick fog. Gravitational waves and neutrinos would also be scattered or absorbed. Gravitational waves and neutrinos pass through matter generally, but if the density reached the level found in the core of a collapsing star, the neutrinos would be trapped, leading to violent continuous instability. 3. End of motion and collapse. Any object currently in motion, the Earth orbiting the Sun at 67,000 miles per hour, or the Sun orbiting the galaxy at nearly 500,000 miles per hour, would immediately slow down due to unimaginable friction. The lack of rotation would also lead to global disaster on planets, dramatically changing climate and ocean boundaries. More violently, the matter of all stars would be surrounded by incredibly dense fuel, leading to instant and runaway accretion onto black holes, causing massive perpetual quasars and supernova, quickly destroying the galaxies themselves. The universe would be a short, violent phase of explosive collapse. The profound emptiness is therefore the stabilizing force of the universe. It protects structures from thermal death, permits the transmission of information through gravitational and electromagnetic waves, and ensures that matter accumulates slowly and locally, leading to the long, measured lives of stars and galaxies. We have covered the fact that space is fundamentally defined by its profound emptiness, an active vacuum that is millions of billions of times less dense than the air you are breathing. We saw how this vacuum allows light, neutrinos, and gravitational waves to travel largely unscathed across cosmic distances, letting us observe the universe's earliest moments. The emptiness prevents constant galactic chaos, ensuring that when galaxies collide, stars rarely hit due to the vast distances between them. But this cosmic truth is often masked by the blinding light of the universe's minority of matter. We see the dramatic effects of gravity, like the motions of stars around the invisible, central black hole of the Milky Way, or the extreme density of matter just outside a black hole's event horizon. It is this immense gravity that converts a tiny amount of matter into incredible light and energy through accretion, a process far more efficient than nuclear fusion in stars. This activity seems to fill space with light and power, but it is just concentrated action within an otherwise empty stage. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. Ultimately, the emptiness is what keeps the cosmos stable and vast, regulating the growth of massive galaxies by allowing black holes to self-regulate their feeding through energetic outflows. If the surrounding space were suddenly dense with matter, the universe would become a place of catastrophic collapse, runaway star formation, and instant destruction. The vacuum of space is not passive, it is the critical condition for the beautiful, long-lived, and understandable universe we inhabit. If you are interested in another consequence of extreme gravity that changes our entire perception of reality, then click here to see this video on why time slows down near extreme gravity.